This PowerPoint has just 3 learning objectives, but the first one covers a lot of territory. It says that you should be able to relate the free energy change to the reaction quotient and the standard free energy change to the equilibrium constant through a consideration of free energy as a state function that varies with partial pressure. Let's unpack this learning objective a little bit at a time. First, we'll examine the idea that free energy varies with partial pressure. Why should that be the case? Well, it turns out to be a consequence of the second law of thermodynamics, which tells us that spontaneous processes are always associated with an increase in the total entropy. Think back to the very beginning of our discussion of entropy. At that time, we all agreed that if we had a gas initially confined to this cylinder, and then we opened this stopcock, the gas would spontaneously spread out to occupy the entire apparatus. Since this is a spontaneous process, the second law tells us that it must be associated with an increase in the total entropy. And if we stipulate that the apparatus is an isolated system, then we know that the spreading of this gas must be associated with an increase in the entropy of the system. So that tells us that an increase in the volume occupied by this gas increases its entropy. As the volume increases, the partial pressure of the gas decreases. Therefore, we can conclude that as partial pressure decreases, entropy increases. So far, we've only focused on entropy, but our goal, as you'll recall, was to determine the relationship between partial pressure and free energy. So what does any of this have to do with free energy? Well, remember that the total entropy change is equal to the negative of the free energy change divided by the temperature. So if entropy depends on partial pressure, then the same should be true for free energy. Accordingly, this derivation shows that as the partial pressure of a gas increases, its free energy also increases. So returning to our learning objective, we've now determined the relationship between free energy and partial pressure. But how can we use this information to derive a relationship between free energy and the reaction quotient, and between standard free energy and the equilibrium constant? Here we have a generic gas phase reaction in which A moles of gas A react with B moles of gas B to form C moles of gas C and D moles of gas D. We want to know the free energy change for this reaction, but since the reactants and products are not in their standard states, we cannot use any of the procedures we've learned so far, such as calculations involving standard free energies of formation, since these procedures yield the standard free energy change. But remember that free energy is a state function. So if we can find a path between the reactants and products for which we know the free energy change of each step, then we can just add these free energies together to get the overall reaction free energy. This diagram illustrates just such a path. In step 1, we take the reactants at the desired partial pressure and change the pressure to the standard pressure, namely 1 bar. In step 2, the reactants at standard pressure then react to form the products at standard pressure. Finally, in step 3, we change the pressure of the products from the standard pressure to the desired pressure. It turns out that we know how to calculate the free energy change for each of these 3 steps. To calculate the free energy changes for steps 1 and 3, we use the relationship that we just derived for the dependence of free energy on partial pressure. In step 2, all the reactants and products are in their standard state, so the free energy change for this step is just the standard free energy change, which we already know how to calculate. So if we add together delta G1, delta G2, and delta G3, and do some rearranging, we can show that the reaction free energy equals the standard reaction free energy plus RT times the natural log of this ratio. If you look carefully at this ratio, you'll see that this is just the reaction quotient Q. So the final expression is delta G equals delta G naught plus RT times the natural log of Q. At equilibrium, delta G is 0 and Q equals K. If we make those substitutions, we discover that the standard free energy change equals minus RT times the natural log of the equilibrium constant. So using this equation, we can determine free energy changes when reactants and products are not in their standard state. And using this equation, we can calculate standard free energy changes from equilibrium constants and equilibrium constants from standard free energy changes.